ideal scenario. So if you're going into a place with less annual radiation, you're going to get less power through that panel. And because the inverter can only convert what is generated by the solar, if the panels are generating less power, the inverter has to do less work, less power. In other words, even if you had 1 kilowatt peak of solar panels, doesn't mean that the radiation is enough for those panels to produce that 1 kilowatt. And therefore, the inverter will not see that 1 kilowatt of DC power. And therefore, if it doesn't see that 1 kilowatt of DC power, it doesn't need to convert 1 kilowatt of AC power. So that 1 kilowatt inverter is doing less work, theoretically. So if you had 90% power through that process, you're only needing to, that inverter is only needing to convert 900 watts in the case of a 1 kilowatt inverter. In this case, you might want to add some extra panels to compensate for this. So yeah, that's why you would overrate the first case. The next reason is pretty similar to the first reason. The actual DC power is not getting to the inverter's inputs. You have possible shade buildup on the panels from dirt that could be reducing the power that is getting to the input of the inverter. And as I said, it can only convert what it is given. You also have power loss on the cables, the connections into terminal blocks, MC4 plugs, etc. You have all these things that down the chain, it loses power as it goes through, which gives you another reason to possibly overrate the inverter, the DC to the inverter rating. Another one to think about is, we know that the efficiency decay of panels, as panels age, their efficiencies drop. So a brand new panel might convert its radiation at a close to 100% efficiency. However, as time passes, that efficiency drops out, and after 25 years, you could see it closer to 80% efficiency. Obviously, when we're designing systems, you generally look at worst case scenarios. So you would look at the higher range of things. I'm going to need my laser pointer later. Is there any laser pointer? Can anyone see this? My mouse? No. Oh, yeah. Lizzie, just tell me in WeChat if you can see the laser. That would be quite useful. Yeah, so obviously, whenever you're designing anything, you would consider the worst case scenario. So looking at this, you would consider the higher efficiency and not the lower efficiency. However, I spoke about how our protection for overrating is so good that this shouldn't become a problem. Zaya, here I see you've raised your hand. Would you like to speak and ask the question? Okay, no? Okay, I'll continue. So yeah, you can consider using, this would be another reason why you would overrate, because you're actually only getting, after 25 years, closer to 85% from that same string. Now we are going to get onto the more exciting reasons for overrating. The radiation on a panel is the function of the distance between the sun and the panel. The kilowatt peak value on the panel is when the solar radiation is at its peak. So if you've got a 3 kilowatt peak panel, that is when in the middle of the day what you're generating. So yeah. This peak is only experienced for an hour or two in a day. So most of the day, the inverter is not working at close to rated power. It's not converting as much as it could. This is nicely shown in the graph on the left, where you can see only in the middle is it getting close to the rated power. For this reason, we could put on extra panels to shift the power profile up the y-axis. By doing this, you're getting the nominal power of the inverter for a longer period. So you're seeing here, you're getting it for a longer period. However, I must reiterate this again, you are losing power here. If we consider the case of the inverter doing only 100%, not 110%, for all those hours in the middle, that power would have been lost. It cannot be gathered back at a later stage. But it's just the price you pay. You do a whole feasibility study on what is the better, what is going to get more out of the system. So what really helps is the price of panels are relatively cheap these days. So this often becomes feasible and useful to do. Even better than overrating it all at the same time in the day is having your peaks happen at 2 different times of the day. Since most of our inverters have independent trackers, you can put a portion of the PV on one of the tracker and the rest of on the other tracker. Or if you have multiple trackers, you can spread it out evenly. By doing this, the inverter doesn't have to convert all the power at the same time. For example, if you have a 5 kilowatt inverter, you have 3 kilowatt peak of solar panels facing east and the other 3 kilowatt peak facing west. In the morning when the sun is rising, the sun is shining more directly on the east facing string. That string could be generating the full 3 kilowatts, whereas the west facing string will not be at the peak and the inverter will not need to convert the full 6 kilowatts. It will obviously be less. And then conversely, or in the same way, in the late afternoon, you will see that the west string will be peaking, whereas the east will be dropping away, as you can see in the graph. This slide just shows us and reassures us that oversizing is allowed, and we design these inverters with this in mind. We overrate all the relevant components that are in the conversion stages, as well as have excellent heat dissipation. Components are always concerned with heat dissipation. If the component can dissipate the heat, it can handle the power, so it will operate for a good time. It is interesting to note the inductors, the new design of the inverters. They've moved the inductors outside the main chassis of the inverter. So all the components inside the inverter, the critical components, are inside this part of the inverter, whereas the inductors are placed external to the inverter. This is a great design. It allows us to also overrate the inverters by even more and run comfortably in overdrive. Different regions obviously have different amounts of average radiation, and this helps us decide what is an acceptable level of overrating. I didn't mention this, but we do not allow you to just overrate to any ratio you like. You can't just put 6 kilowatt peak of panels on a 3 kilowatt inverter. That's an overrating of 2, and that's too much. In my mind anyway, maybe we can talk about it, but that sounds too much. The table shows us what the ratios we allow. You need to check the annual radiation for the region the installation is going, and then check the table. I expect a question here, or I'm at least thinking of a question here. Annual radiation versus peak radiation. So for example, in the UK, in the winter periods, we get a very low radiation count, and in the summer it compensates for that in a large way and gets a lot more radiation. And so we would experience higher peaks, but our average is pulled down significantly due to the winter periods. So, and our inverters are really, I mean, you would really think about the peak radiation over the annual radiation, because in those summer days that the radiation is high, the inverter's got to do that. And it's for a long period of time. It's for a solid day. So it does need, in theory, I would prefer to use a peak radiation value. However, to counter my own point, these values, our inverters, the inverters are so well designed that these over rating ratios are extremely safe, and we can rely on them. And it's also quite hard to get peak radiation values. So, you know, that's also a little bit of a struggle. Anyway, yeah, so that's the end of that first section. Any questions? I don't know how I'm going to answer them. Will you send the presentation afterwards? Yeah, so I'll speak to Lizzie. I think the recordings are going to be updated, all the presentations. The recording. I don't know if we will share the actual presentation. Okay. Our inverters don't have a large, heavy transformer inside of them. A transformer is a device that converts AC voltage from high voltage to low voltage, but the main advantage that you get from it is galvanic isolation. Between the DC, your solar panels, and your AC. Our inverters don't have a transformer, so there is no isolation between your solar panels and your AC grid. Transformers in PV inverters like this are not worth it. You lose efficiency. The inverter becomes extremely heavy, and there is really no need for it. It works perfectly without a transformer. These connections through to earth really shouldn't be on a system. In an ideal case, in a proper installation, you don't have these problems. So there is no need for galvanic isolation. But because there is no galvanic isolation, any connections on the DC side of the system, so where the solar panel is, any connections through to earth on those conductors will be shared directly through. These switches are switching regularly and very quickly, as well as these reverse diodes. This is alternating voltage, so these could be forward biased. You would see that would be transformed onto your AC grid, and we should know that you can't just connect earth to a live wire. It's going to be a lot of current, and you're going to be very unhappy. Yeah, so I have seen before when connections have been made while the inverter is running on the DC side, and large currents flow, and it has caused circuit breakers to trip, flash across circuit breakers, very, very scary stuff, which of course we can understand would cause damage to internal components. So our IGBTs inside the inverters, this current flows through this whole circuit, so you will see damage on IGBTs. Each inverter has really, really good trial and tested overcurrent protection, short circuit protection, which you would think should protect against this high current phenomenon that I've just spoken about. You can even short the output of the inverter and it will survive that. It's got short circuit protection. However, due to the reverse diodes in the IGBTs, so if you look at both diode 1 and 3, those will go into forward biased mode if you have a positive voltage relative to earth on the live. So if your L on the grid is higher than your neutral, which it's quite 50% of the time it is, which is connected to earth, you will see that those will go into forward bias mode and there will be a lot of current flowing through. So even if those switches opened up fast enough, which they do, because we've tested short circuit protection, a lot of current still flows through the diode, which is very little resistance, which causes a lot of current and a lot of damage. So that's when the damage is occurring, as hundreds of amps are flowing, generally causes circuit breakers, your mains circuit breaker to trip and flash across. And I mean, the inverter tries to save itself as well. it opens up relays, but those relays are rated for 200% of rated capacity. If it's a 1 kilowatt inverter, that's like 4 amps. 200% of 4 amps, 8 amps. You're looking at an 8 amp relay, 100 amps because of the fault running through that relay. It's going to weld shut. So yeah, even if the inverter detects it in time and is fast enough, which relays aren't fast enough because they take 20 milliseconds, it cannot do it because it will weld shut. So yeah, that's the problem. Because this is such a big problem, obviously the inverter must not start generating into this problem. Therefore, we have a detection circuit that detects any low resistances to earth on the DC before it operates. But again, let me reiterate this. If any fault occurs during operation, for example, you drop a conducting driver across an open DC connection to earth while it's operating, the inverter can't protect itself, and the circuit breaker will also not be too happy. The detection circuit works by measuring the voltage between the PV positive and earth. And then in another time instant, it measures the voltage between PV negative and earth. The measurement circuit inside their inverter forms a voltage divider with these resistances. And if the output of that voltage divider is higher than 20 volts, you know that you've got a low resistance. So ISO 1 or ISO 2, depending on which one you're doing, is low. Yeah, so so before it closes its grid relays and starts generating, it does this whole check and makes sure that there's no weak connection. PV isolation faults are only a function of resistance, whereas your eye leakage faults can be a function of capacitors too. Thank goodness I'm not doing my presentation on eye leakage. It's quite a headache. It's an interesting fault to deal with. So yeah, maybe in the future. Probably the most common occurrence of this is broken DC wire insulation. The insulation is points 2 and 3 in the figure. If this is broken or cut into, there will be no problems immediately, because air is in fact a very good isolator. So you, in theory, could have just the 0.1 running along the system, but if anything does touch of it, and obviously things are floating around the air and things can touch it easily, you will run into a lot of problems. So yeah, air is a very good good isolator. However, if any conductors connect to earth, comes close to it, it would cause this issue. This often happens at 90-degree turns for steel trunking, where the edge forms a sharp edge, and generally the trunking is earth. So when that cut is made, the steel makes a good connection through to the conductor in the middle of the wire, and it causes a nice, strong connection through to earth. Also on rainy days, the water could get into this new gap, this new hole, and cause a lower resistance to earth. I've also found that water buildup in MC4 connectors can cause these faults. I've had a couple of systems where I've had calls on, and we've investigated and using methods I'm going to show you now. We found out which string it was, and they found and which pole of that string it was on. And then it turned out it was just an MC4 connector. So yeah, and water and moss buildup in the MC4 connector. Replaced the MC4 connector and everything was good. If you're getting this alarm on this inverter, I would suggest trying each string individually. It is unlikely that all the strings have the same problem. It will be quite strange unless it's been left like that for a long period of time. Yeah, so that's a very nice, quick, easy test to perform. Another test to perform is measure the voltages between PV positive and earth, and then again PV negative and earth. This is the same test that the inverters do. Doing this test, you can actually find out which pole the fault is occurring on. If you're getting a high voltage between PV positive and earth, obviously the connection is, the bad insulation problem is on your PV negative pole. And conversely, if the high voltage is on PV negative to earth, your connection is on PV positive. Then finally, the solution, if you have a nice expensive isolation tester, then you can use that to measure the insulation resistance. Please note that if you do use this, please make sure that you have your earth connection or your earth probe plugged in. Having it floating is useless. It won't get you a result. You will always find high resistance and you basically doing nothing. This is still an issue with the installation side. Earthing your PV side doesn't really help remove this issue. It's actually just a safe to-do thing. You don't want floating conductors in your installation, so just make sure that you're earthing all your conducting items in your installation. However, the earth to the inverter is very important for this. If your earth to your inverter is floating, your detection circuit doesn't have a solid reference to compare with, and you will get nuisance tripping. You could get nuisance tripping, or you could get fail to detect results, which would cause the inverter to start generating into this fault and make everybody very, very sad. The final reason you could be getting this PV isolation or ground fault is inside the inverter. If the detection circuit is faulty, as I alluded to earlier, if your earth reference is floating, which is actually not really the inverter's fault, you just, it won't be able to detect that fault, and you just need to make sure that the connections are properly made towards your AC earth. Or if the MOVs inside the inverters are making a connection through to earth, you will see this fault. MOVs are variable resistors that decrease resistance when they have a higher than rated voltage put across them. So it sounds like a weird component to put in your inverter. There's very, very good reason for them inside the inverter. They act as a surge protection. If a high voltage is put on the DC input or even the AC inputs, but let's just talk about the DC inputs. The MOV will see this high voltage and decrease its resistance down to earth. I'm talking about higher than rated. So 1,500 volts, for example, it's a surge of voltage. This MOV will see that and it will drop its resistance and hopefully be able to bring down that voltage spike and keep everything safe. But we got to understand that these MOVs are a component that can only take in a certain amount of energy. And if it gets, for example, hit by a lightning storm, it won't be able to handle that and it will blow into short circuit. And that's when you get this problem happening. It's couldn't handle the energy that it had to dissipate. It went into short circuit and it's forming a strong connection between MPPT input, one of your DC conductors, through to earth, and you'll see a PV isolation fault. With this fault, however, it is easy to investigate, easy to find. All you need to do is connect your multimeter up, and then measure the resistances between each MPPT input and earth. And if it's not significantly high, if it's close to zero, then you've got a problem on there. It's usually the MOVs. So yeah, that's the end of that section. Any questions? Okay. The final section. Okay, PV systems have a DC side and an AC side. So that's the point of an inverter. It converts your DC to your AC. And the cable selection process is slightly different for each. On the AC side, we have two materials that can be used. Your copper being the better one, lower resistance and higher current carrying capacity. But you got to pay for that, so a bit more expensive. And then your aluminium cable, which I seldom see getting used, which is a good thing. Copper is just generally a better material to use. Your AC cables, you often see the phases all bundled together, so multiple cores in a single cable. That's absolutely fine, as long as they've got isolation between each of the phases, so that's all good. Whereas the DC cables, you don't really want to run them all in a single cable, multiple cores in a single cable. Just it brings up phenomenons like parasitic capacitances and annoying things like that you really don't want in your system. Extra headaches that you got to analyze and work out. So yeah, single cables for DC are generally a better idea. Generally, your DC or PV cables run outside or on top of the roof, therefore hit by bad weather conditions. A good insulation that is designed for this should be considered, and maybe, if possible, trunking would be a good idea, especially running through a building. The main three things to consider when designing your PV cables: the insulation must be able to handle the voltage on the cables. However, there's a little bit of an interesting point here. Even if you have 100 volts DC on the PV, you would think you just need to rate the cable for 100 DC, but you generally, your surroundings are earthed, and that could be running at 240 volts AC. I'm guessing. I need to think about that one a little bit, but about 200 volts AC running on that earth relative to your DC conductors, and therefore you would need to have your insulation at least able to handle that. Next, you need to make sure that the cable can actually handle the current. This is really, really important, the most important. You don't want molting cables, obviously. However, generally the voltage drop, the next point, comes into a problem before the current handling capacity. I like to use a rule of thumb of 4 amps per millimeter square. So if I've got 2 strings in parallel, say my strings are MPPT currents of 8 amps, or just less than 8 amps, just to make this, because it was always over design, right? So let's say 7.5 amps each. I've got 15 amps on running through that system. I would need to design with a 4 millimeter square cable, because then I've got less than 4 amps per millimeter square. And finally, you need to consider the voltage drop. The inverter doesn't really get influenced that much by the voltage drop on the DC side. However, you will come into efficiency problems if you don't consider it. We're more concerned with the AC side voltage drop, which is what we're going to talk about now. The AC cable, we're only talking about the AC cable between the inverter and the mains incoming grid connection into the installation. Again, we have to consider the design specifications. You need to make sure that the cables can handle the voltage again, but this time it's AC. AC is a lot easier to handle. Generally, you'll see that your AC voltage ratings of insulation is a little bit lower than your DC, or higher, sorry, because it's dropping up, going up and down, up and down, up and down. It kind of gives you like a release mechanism, so it's quite nice. Also, getting shocked from AC is a lot better than getting shocked from DC. The cables need to be able to handle the currents. That's an obvious one. On the next slide, I'll go through some quick calculations on how to calculate this. Temperature of the cables need to be considered here, as you often run the cables next to each other or underground or next to something that can dissipate heat, and that will always have an influence on the amount of current that cable can handle. However, your cable manufacturer usually gives you good data on how to work this. They give you a table and they tell you how many cores you're running per conjugate or in conjugate, etc., and it's usually quite easy. And then lastly, this is the most important one for the AC side, is the voltage drop of the cable. Because the cable does have a resistance associated to it, when it's got a current running through it, it's going to have a voltage drop over it. And if that voltage drop is too high, the inverter will see a much higher voltage than is at the transformer, where the loads are. Where it didn't need to disconnect, it will disconnect or stop or generate less power. So yes, you need to make sure that that cable running between the inverter and the grid connection is sized correctly, and that you have less than 2% drop. The last one, the voltage drop, often gives us technical support guys a headache, because if the cables weren't designed properly, then the inverter reports that overgrid voltage alarm, and everyone goes straight to the inverter being the issue, where in fact it is clearly a design fault. So yeah, as I said, when designing the AC cabling for a system, the first parameter you need to find is the maximum current that will be put through that cable. The formula for current is the power going through the cable divided by the voltage on that cable. Single phase systems are easier because all the power is running over that single phase. However, not that much more complicated in three-phase systems. You just need to divide the total power by 3 to get the per phase power. For example, to ease up my brain on the math, let's consider a 6.6 kilowatt three-phase inverter. We want to know the current on each cable for that. The per phase power is that divided by 3, which is 2.2 kilowatts. Then we consider the worst case scenario voltages because we're smart, which is 220 volts. We are injecting power, so I doubt it would be that low, but let's just consider 220. You get an answer of 10 amps. So 10 amps will run through each of the conductors for that three-phase system. Now again, this is a rule of thumb. You multiply that number by 1.25, shown in the previous slides. I showed it in the previous slides. Yeah, 1.25 in 2. And the reason for this is clear. We definitely do not want our circuit breakers to trip. And as we know, we always design our circuit breakers to protect our cables. So the circuit breaker has to trip before the maximum current of the cable is reached. Okay, so if this is the example of a bad problem, if you don't use that 1.25 factor, if you design your cable to handle that 10 amps, you will need to put a circuit breaker on there that trips at 10 amps or lower, so 9 amps or 8 amps. And if in the middle of the day when that system's generating, you're going to get that inverter getting to 10 amps per phase, and it's going to trip that circuit breaker because that circuit breaker is rated at 8 amps, and you're going to get no grid alarms on the inverter. So yes, always consider that factor that we multiply by 1.25, so you would get 12.5 amps, and then you can design your circuit breaker at 11 amps or 12 amps, just so that it's above your maximum power that your inverter can inject. Okay, now I was given this slide to present. It looks complicated and rather messy. It shows you how to calculate the resistance of a cable and therefore the voltage drop for that same cable. However, generally the cable manufacturer should be giving you a value of resistance per meter or help you out a little bit. Also, we and many others have online calculators that calculate this for you. One thing to note is to always consider the complete path of the circuit. For single phase and three phase, it is twice the distance between the inverter and the grid. I know in three phase systems, the return path is over the 2 other phases, but it's half the time over the one and half the time over the other. So you can just consider it as twice. But yeah, so yeah, that's that slide. And yeah, excellent. Thank you for watching. Any questions? So let's see if we can get these questions out properly. Okay. Hello. Okay. Yes, yes, yes. Yeah. Okay. So isolation tester, not a term used in the UK. We call it a multifunction tester. AC cable colors are odd colors. Please show harmonic cable image in future. Okay. So it's not a question. What is Christopher's question? Okay, so yeah, I didn't mention enough about that. Yeah, so you can set the value at which the inverter detects its PV isolation fault at. You just go to advanced settings. Let me share that back. Yeah, so you just go to advanced settings, special settings function, zero compensation, and then you can set that value. But generally, I mean, the default value is in the region of 200K or 150 kilo ohms, which is a pretty high value. And if you are getting in that region or lower, it's quite easy to get higher than that value. So I would suspect, in what's going on here? How come I can't time as the presentation? That's Joseph, you asked, is dual core is PV cable or a single core better? I would say a single core is better. So the reason why, and I didn't allude to it that much, the problem I have with running cores for the DC close together is parasitic capacitances are formed, and a capacitor is a function of distance between the cable and the length of the plate. And if you think of the two cables running next to each other, they are forming two conducting plates running next to each other, and you could possibly get a parasitic capacitance formed. However, I'm actually just thinking about that now, and that's forming a capacitor between positive and neg, which is actually not a problem. It's only a problem when it's a capacitor formed between PV and earth. So maybe not, that point maybe was just cancelled.